Welcome to Math 105, Chapter 2.3, where we talk about annuities. What are annuities and how do they work? So think about the money sitting in your bank account right now. You make a series of either withdrawals or deposits over a period of time. These are called annuities. You can either make these withdrawals or payments at the beginning or the end of each period. Now, if you do it at the beginning of each period, this is called an annuity due. And if you make them at the end of each period, this is called an ordinary annuity. Now, because there's a slight difference in the either beginning or the end of either the payments in or withdrawals out, you're going to see a slight difference in the formulas. So, and this goes for our two big formulas that we're going to be working with today. So accumulation. So what does it mean to accumulate something? Just think about it for a minute, let it mull it over. Well, to accumulate something means to collect or grow, which suggests some future value. So we're thinking accumulation is some future value. So if we're talking about having these two different circumstances, let's touch upon ordinary first. And I cannot spell very well, so if you do see a spelling mistake, just make a correction on your end. So ordinary being at the very end of each period says that we have your future value, which is equal to your PMT. This is going to be your payment. If we're trying to accumulate something, right, we want it to grow, are we going to be making deposits or withdrawals? Well, if we want to make it grow, we're going to be depositing money into your bank account. So your PMT in this case is going to be a series of deposits. These can be called your payments or PMT. Now you have your payments, and then on top of those payments, we're going to be having some series of compound interest going on. So we have 1 plus R over M times MT. So that is your compounding minus 1 all over R over M. Again, you might see this formula a little bit differently, either in a formula sheet or in your textbook as PMT times 1 plus I to the N minus 1 all over I. Keep in mind, if you see that, I is just a fancy way to say R over M, and N is a fancy way to say M times T. So everything else stays the same. So R, M, T, those all mean the same exact things, except in these formulas, we're no longer working with a present value or a future value. You're working with a payment, something that you're either depositing or withdrawing. So if this is an ordinary annuity, then on the other side, we're going to have your annuity due, which is the beginning. Which says we have your future value is equal to that payment again. We're going to be thinking that these payments are just a series of deposits. Now, because you're depositing it at the very beginning of each month, it's going to accrue its own set of interest. So there you have your interest on top of that payment times the same exact formula we're going to see before. So there you have it. You can kind of compare the two that you're seeing here. And meaning we don't have to have the compound interest on top of the payment at the very beginning. Instead, we're not seeing it happen until the very end with all of the rest of the account. Now, for those that are using a TI 83 or 84 or kind of any similar of those products, I would definitely use a big parentheses at the end here, or even at the end over here as well. Okay, so if I were to write this out, after I do my payment value times, I would then make one big parentheses. So open, open, open. Do this stuff, close this parentheses, subtract one, close your next set, divided by. I would probably do this in division again, same thing with here, and then close that next one. Okay, so just be super careful depending on your calculator. If you would prefer using Desmos for the remainder, for this one, that's fine, except for those who are taking this class during a face-to-face experience. I do provide those TI 84 calculators, which you are not able to use a Desmos account. All right, so that said, let's try example one. It says at the end of each month. Okay, so they've already told us some context. Are we ordinary or annuity due? Well, at the end, so we're working with this formula. So at the end of each month, you deposit $50 into an account, earning 2% annual interest compounded monthly. Excuse me. Find the future value after 5 years. So notice that they're saying deposit. So we're trying to grow this amount. So we have your payment, a series of deposits of $50. We have a rate, a time, which I can see here is 5 years. We said 2% annual interest, which also suggests years, which definitely do match. We want to keep that in mind. We always want to match your figures. We said M is monthly. Okay, find your future value. So again, they're very specific in what we're trying to find in this case. So future value, we said is equal to your payment times times parentheses 1 plus R over M, MT minus 1, close parentheses, divided by R over M. And I would probably put your formula kind of into this format when you go to plug it into your calculators. So we have $50 times, and I'm going to put it in here as if I were putting into my calculator. So opening up two more, 1 plus 0.02 over 12. So I would probably put this in a series of parentheses as well. So I've opened this one, I've closed this one, which means I've opened this one and now need to close a second set. Raised to the 12 times my 5. So if I've closed this one and closed that one, I've done that. I now need to subtract 1 and then close. So now I've closed this one out, right? Each one you can kind of trace back, divided by your rate over your compounding period. Last parentheses. Oops, let me write that a little bit better and close. Now I'll probably do this first one in a TI 83 or 4, and then I'll show you Desmos on the very next one. So I have 50 times, and this is where if you would prefer to do that, what is it called? The fractional button, where you go to math, and then the frac. So this would be really useful for you guys if you have it. Now I'll show you what it might look like if you don't have it. So I'm going to do my 50 times, and I said we're going to open up 3 parentheses to start, 1 plus, and then my division with my rate and my monthly compounding period. Now I've closed that division, and then I closed the addition of 1. I'm going to raise it to the power of 12 times 5. You could also do it as 60, and then come down to subtract 1. Close that parentheses, and this application is really nice because it's showing you how many are open. If you don't have that, that's okay. Just kind of keep playing with it. So I divide, and one more time, I'm going to do my rate divided by my compounding period, and then close 1 more. Now, if you opened one and didn't close it, you're gonna get up an error that says syntax error. That's likely because you didn't finish it out and your calculator doesn't know how to read it. So here we have $3,152.37. And there you go. So I would say pause the video here, see if you can practice the next one. It says find the future value if $200 is deposited quarterly for 18 years at 2% interest per year. So your payment is equal to $200. Your rate is equal to 3%. And this is in years, which can convert to 0.03. We said we're now working with 18 years, not 20, 18. Oh, it's not 3%. It's 2%. Yeah. This is years. And we said we're compounding quarterly. All right. So one more time, your future value is equal to that $200 deposited. And then we're gonna, let's see, did I write it up here? Yeah. One more time, I'm gonna write it as if I'm putting it into a calculator. 1 plus 0.02, 18, raised to the 18 times 4. And I don't know why I put an 18 on the bottom when I know our compounding is for quarterly. Minus 1, close my parentheses, divided by, again, that division, and then close my last one. I just want to double check everything one more time. Make sure I divided correctly. Perfect. All right. Now this time I'm going to do Desmos, and I'm hoping that I have all my numbers in my head. We said $200 times, let's see, I'm going to open up probably a double parentheses here, 1 plus 0.02 divided by 4. And it is nice that it already does that for me where it kind of breaks it up. So one more time, closing that parentheses, raised to, and I can either do, what is it, 18 times 4, or you can multiply those together in your head. Oh, keep in mind though, when you are using Desmos, since I don't use it all that often, I tend to forget that you have to do the little steps. Minus 1, and I want to make sure that yeah. Nope. Minus 1, close parentheses, divided by, there we go. This is going to look very similar, if not the exact same, to what we have on our page. And let's see, we have 201.02. We have 418. All right, let's do it. So we should have 17,281.77. 17,281.77. So that would be your future value of your bank account if you were to make $200 deposits quarterly throughout the year for the next 18 years at a 2% interest rate. So this is really nice if you have your payments and you're figuring out your future values. However, what would it look like if we didn't have your payments, but we had a future goal in mind? So sometimes we need to find your payments necessary to grow an account to a particular amount. Let me make sure. Yeah. So we have your payment. We don't know what this is, so we want to know how much do I deposit to get out my future value goal. Now, we could derive it if we want. It just takes a minute, but we're going to multiply your future value by your rate divided by your monthly or your deposits, not just monthly. 1 plus R over M times MT minus 1. Okay. So this is going to be our new formula anytime we go to make a series of deposits. So let's try this example out. Example 3. It says, find the periodic payments necessary to accumulate to $20,000 in a fund paying 6% per year with monthly payments for 5 years. So we are going to use this. We said we have your future value of $20,000 in a fund paying 6% per year, which comes out to 0.06. T is for 5 years. Again, they match. This is really nice, less work for us. And we are looking at monthly payments. So I'm going to write our formula one more time. Future value times R over M over 1 plus R over M to the MT minus 1. So what this is going to look like, we have $20,000 times your rate, 0.06, over your compounding monthly. I would put this in parentheses, divided by, open up 2 parentheses here, 1 plus, again, that same division, close those parentheses, raise to the 12 times 5, I believe. And then minus 1, close parentheses. Now, one thing that I didn't do at the beginning, which I think it's not the end of the world if you don't do it, but I like to put an extra pair of parentheses here. I think it looks a little bit better, but again, not super necessary. So I don't need to include it if we don't want to, but I do think it tends to work a little bit better. Oh, and I never actually put it in. I was just ready to move on. We said $20,000 times, and I'm actually going to do the fractional button again, or actually this time to show you what it looks like. So you can actually do a double fraction if you wanted. So if you wanted it to look something like this, we have 0.0, or I already forgot. I think it was 0.06. We said monthly, close that parentheses, divided by 2 parentheses here, 1 plus that same division. And you could have, or I could have done that fractional button here again, which I might just make it look kind of nice. 0.06, show you all of your options. Close that parentheses. No, there we go. Raise to the 12 times 5. I believe our time was 5. And I'll double check everything before I finish and close that out. Again, I could put a big parentheses at the very beginning. It shouldn't matter though. Let's see. I just want to check my values. 12, 5. Gotcha. Go ahead and hit enter. So my deposits would have to be $286.65 or 66 cents. 286.66. 286.66. So this would be my monthly deposits for a 5-year period at 6% interest rate if I'm trying to grow my account to $20 or $20,000. So that is out of the way. We now know your future value, how to get your payments to kind of go back and forth. Now we want to go in the opposite direction. So it says previously we calculated how much we can accumulate into the account or its payments to accumulate. In order to accumulate, we make deposits. Right? If we want to make something grow, we're going to deposit into it. So then what is the opposite of a deposit? This would be a withdrawal. Again, I can't spell, so I think that's how you spell it. Therefore, yeah, that is. Therefore, instead of working to accumulate or grow an account, we start with our present value and make a series of withdrawals. So in some of these problems, all you have to read is the context. Are you trying to make something grow and therefore deposit into it? Or do you have something now that you're going to be taking away from? So just think about the bank account that you might be having right now and what you end up doing on a daily basis. So again, we have two different formulas because we have two different scenarios. One being ordinary, which is at the end. This has the formula PV, or present value, of your payments. And instead of being deposits, these are now going to be, oops, sorry, I intend to write what I say. These are going to be with your withdrawals. Times, and because they're similar ideas, their formulas are also going to be looking very similar. So instead of taking your compounding interest and then subtract by 1, we're actually going to do the opposite. 1 minus your compounding. And then you also have a negative rate up here divided by R over M. So this is what it would look like if it's at the end of your account. But let's see what it looks like if we do it at the beginning. Okay. You'll notice that a lot of the times we're going to be using the ordinary, the end value. We just have so much to do in our class that I kind of just stick to the same ones every time, but just know you would just tack on an extra compounding period. That is the only difference when it comes to these formulas. So there's that extra one, and then it's the exact same formula. And there you have it. All right, so if you want to give it a shot and try to enter it in, because a lot of this stuff is really just giving the formula, entering it in. Give the formula, enter. So I would pause here and see, just give it a shot. So example 4, it says at the end of each month. So again, at the very end, telling us we're doing ordinary. You want to withdraw $50 from an account earning 2% annual interest compounded monthly. You want the account to last for 5 years. What is your present value? So if we are trying to make a withdrawal now, our big context of this problem, instead of asking for deposits, we are now working with withdrawals. So a lot of these problems are going to give you some keywords, that being one of them. So we are now withdrawing $50, and I'm going to write withdraw. So $50 at a 2% interest rate a year, so 0.2. Your time being 5 years. Again, super nice that these match. Oops. M is equal to 12. So we're going to throw that into your formula. Your PV is equal to your $50 times, and because we're working with the value at the end of each month, we're going to be working with ordinary. So opening up 1 parentheses to start, and then 1 minus 1 plus 0.02 over 12 raised to, again, the negative 12 times 5. That all looks good. And then let's see. So kind of keeping track can be hard if I'll start from here. I opened, I closed, I opened, I closed, I opened. Now I need to close this amount. Divided by 0.02, 12, and then big close. So at the very end, it is super important to put this last one here. This is the most important one. If you don't do this part, I think your calculator will know what it's working with, but this one is the most important one to close. So let's punch this into, I'll try Desmos this time. So we said 50 times 1 minus 1 plus 0.02 divided by 12. Oops. You can definitely tell I don't use Desmos. It's not my preferred calculator. A negative, and I think the negative button here is just a minus sign, 5 times 12. Now, if you're doing it on the graphing calculator one, you should be using the negative sign, which is found right next to the enter button as a little like decimal point. If you use the subtraction sign, it'll come with a syntax error, which means that it's just not reading it correctly. All right, close that parentheses, divided by 0.02 divided by 12, close this parentheses, and then close that one. I'm going to reread, just make sure I have everything in its spot, and I'm going to go ahead and hit enter. So we get 2852.62. So this would be your present value. So if you're making a $50 withdrawal over this context, your present value has to be this much. Now we can also go in the reverse. So we want to know your present value. So sorry, we have your present value. We want to know, well, how much can we withdraw until there's perhaps nothing left, right? So we are going to do your payment, which again is just a series of withdrawals in this case, which is equal to your present value times R over M divided by 1 minus 1 plus R over M to the negative MT. So it's kind of the reverse of what we've been seeing. Again, you can do a bigger parentheses around here. It won't make a huge difference though in some of these problems. Just be careful with this negative sign. Use a negative. Use the negative sign with using TI-84. All right. So again, see if you can pause the video and try it out yourself. It says, what is the amount of money that should be withdrawn? So we don't know with your withdrawals at each quarter from a $100,000 college education fund, earning 4% annual interest compounded quarterly in order to get to the account to zero after 4 years. So they're telling us how much we have right now, and we want to know how much can I take out? So your present value is 100,000. Your rate is 4% a year. Your time, we said, was over the course of 4 years. And I think we're doing quarterly. Yes. And making sure that these, so sorry, that these match. All right, so we have your payment is equal to your present value times your rate over your compounding period divided by 1 minus 1 plus, again, your rate over your compounding period raised to the negative, and I'm actually going to put that in red again, negative 4 times 4, and close your parentheses. Again, kind of tracing back your parentheses, we have this set of parentheses, this set of parentheses, and this one. This is the most important one that you have to include. I'm going to punch it into this one this time. So we have 100,000, just counting up your zeros. Math, fraction. What I hate about this is that it gives me some adds on this thing. 0.0, was it 04? Divided by 4. Let's see, 1 minus 1 plus 0.04 divided by 4. I'm going to double check before I hit the enter button. And notice that I'm going to be using your negative button. So right next to your decimal place or right next to enter is that negative that we're looking for. And I want to say we were doing 4 times 4. Remember there being a lot of 4s in this problem. All right, I just want to double check everything. 0441. Separate the numbers and fractions. Multiplication. Oh, so in this case, if you're using your fractional button with, this is actually really good. If you're using your fractional button with some of these newer calculators, what this means is that notice how the ones above it, I'm using the multiplication symbol. I forgot to use it here and I need it. This one is just a little pickier. I think you could get away with it if you did do the parentheses around this whole thing, but don't quote me on that. There you go. So we would have to make that sort of payment. Let's say I just want to double check that I made everything correctly. Yeah, here we go. Ooh, 679446. 67. Oh, I know I'm going to forget. 6794.67. I think is that decimal. Let me just double check how easy is that. 4, 6. Not even close. 4, 6. Okay. All right. So a little bit more extra credit. Again, either submit your answer and work to me by the next class. If you're in person or if you're in a summer class, please submit it either to week 1 or week 2, depending on when you're getting to this video.